welcome back. Our talk this time will be talking about internal forces. This is part 2 in our series, and in particular we'll be talking mostly about the sign convention that's used and how we can use that sign convention to write some basic equations that describe the internal forces of beam members. So what we have in this process, for the sake of our example here, we're going to talk about a simply supported beam, all right? And as is indicated here with internal, okay, we're wanting to know what's going on inside of this member. Now, maybe I have a load that is, applied something like this. It could be some variable distributed load. It could be a point load, whatever the case may be. If I'm the designer of record for this beam, I want to know what the worst effect is and where it occurs in this beam. All right. Now, for starters, we're going to take a look at how do I determine what these internal forces are and how do I start to generate some of these relationships that we need to be looking at. All right. So the sign convention that's typically used to define this becomes rather important for us. Okay. So we're going to start off, we're going to talk about the shear. Now, if you remember, the shear was the one that occurred if this was, you can kind of see it, we got a little bit of lighting, was the one that occurred parallel to the face that we were cutting. All right, so the way that we draw this, and I credit this to a statics professor I had many years ago that kind of helped me with these pictures, and to this day, it stuck with me, the sign convention. All I'm going to do is I'm going to extend this cut line as a dotted line, okay, and if I have my cut line, if I draw my arrows on the left side of the cut for shear, up is positive, okay? And likewise, if I draw to the left of this cut line, again, that's the dotted line that's here, down is positive. All right, so what that means on the entire beam, depending on which end that you work, and remember, when we talked about internal forces back with truss members and axial forces, depending on what side of the beam you are on, a positive could be one way on one side, but it could turn around and be positive and going the other direction on the other side. Okay, and it's the same kind of idea here, but it's just not quite as intuitive as it is with the tension and the compression. All right, so what we do is if I take my beam and I cut it, again, maybe I'm only looking at this left half. Well, then the positive sign convention for shear is the beam with all of its loading and all of its support reactions and everything I want to include, and the shear acting down. Okay, and that's again because I cut it here. And so I'm going to be writing these letters and these arrows to the right of that cut line. So if I come back over here, here's my cut line. To the right, it's this guy. All right, that's the positive. And likewise, over here, the cut is on this end. And now I'm writing to the left of that. So now I need to be taking the positive to the left of the cut. And that's this guy. So that's why it's up. Okay, this is probably the trickiest of the bunch. Okay, now the next one then we can talk about is our moment. Okay, and this one's pretty easy to remember, really. All we're going to do is we're going to picture a beam, and I'm going to put a cut line on the left end of the beam, and I'm going to put a cut line on the right. Okay, and you can kind of start to see where we're headed with this, all right? So if I'm putting my arrow to the left of the cut, clockwise is positive for moment. Okay, and if I put it to the right of the cut, counterclockwise is positive in the moment. So what does that mean for our example where we cut it before? If I look at this half of the beam, counterclockwise, positive, because I'm writing to the right of that cut line. Okay, and so here's my cut line, and the one I want is on the right of it, and that's this guy that's counterclockwise. And likewise, on the left, if I draw it now, I'm writing on the left of it. Okay, and so for the other half of the beam, a clockwise moment is considered positive. So it kind of depends on which end you start with and which piece that you want to be working with at the time. Okay. Now, most of the time when we go and we do our internal forces calculations, especially with shear moment diagrams and those kind of things, what we're going to do is we're going to start and we're going to work from left to right. Okay, that's just for almost all beam problems, that's just kind of the way that it's done. And with that, you'll get in the habit of being able to see these, and you'll start noticing that it's this first picture is the one that we typically start to draw, whether it's this moment one up here or the shear one that's here. All right, now, my statics professor back in the day gave me a saying that kind of helps me remember this, the sign convention, especially for the moment. All right, so if I imagine this beam, and I know in statics we say everything is rigid, but if we were allowed to allow this beam to deflect under these rotations on the end. If I take the end of this thing and I kind of bend it that way, clearly it's going to start to bow down. All right. And so all we have to do is kind of draw this deflected shape and put a positive up here and draw two eyeballs here. All right. And she gave me the saying that positive moments make us happy. And that's kind of what you see. See, here's the smile, there are the eyes. And so that's the way that we can always remember which way is which for positive moments. Cheesy, I know, but by golly, it stuck with me for many, many years. So anyway, enjoy that. And okay, the last one that we'll do then is the axial case, and this is the one that we know from our trusses, okay? And basically the axial positive case is the tensile case. All right, so if I have a cut line on the left of the member and a cut line on the right, if I'm to the left of it, I'm pulling away from the member, that's positive for my normal force, or for my axial force. And likewise, if I'm to the right and I'm pulling on it, that's positive for the normal there. Okay, all right, now, what does all this mean? Okay, if I put it all together, okay, as again, all three of these things occur simultaneously. I just wrote them separately so that we could kind of analyze them one by one. Typically, problems we said are worked from left to right. Okay, so if I'm starting over here and working, I don't care this is a cut line, I don't care what's going on over here. But on the cut at the location that I'm interested in, at this point here, okay, the positive sign convention is going to be to the right is in positive, counterclockwise is the positive moment, but the shear is down. Okay, and so shear positive is down, and that's kind of counterintuitive, and that's the one spot that seems to trip people up. Okay, is that one little exception. But if we can remember this guy, then when we go into the next phase of this, which I'll show you in a second, everything kind of works itself out magically by doing that. All right, now if you look at it, if you remember, our usual sign convention from way back with the vectors was kind of a right-hand rule kind of thing, right? I have an x positive to the right, I have a y positive up, and counterclockwise was positive. This guy follows 2 out of the 3. It's the shear that's different, okay? And so that's one way to kind of remember it and tie it back to what we have been working with so far. Okay, all right, so let's give one a try. Okay, and say that we want to be able to find what's going on with the internal forces at a specific point. Okay, and so what I have in this is I have a simply supported beam. I have kind of a roller connection here. It's one of these roller blades with the multiple wheels, but it's a roller support, meaning it only has a vertical up. And then I have a pin support at the right, and I'm putting a point load at 3 meters from A. Okay, now notice it's a 3 meters here and a 6 meters here. I know it's not drawn to scale, but it doesn't really matter. And what we want to look at is we want to be able to find all of the values associated with the reactions, but more specifically, I want to know what's happening at this point B. Okay, now B is just to the left of 6 kilonewtons. Okay, it's at like 2.99999999 repeating. Okay, not quite 3, but right there, 3 for all practical purposes. Okay, and then we want to look at the other side at point C, which is going to be at like 3.00 ... Okay, and so we're just past the load. Okay, so basically these are the same point, mathematically speaking. Okay, so what we want to look at then is let's figure out what the internal forces are at B and at C. So this is the normal or the axial, shear, moment at B, and then we have the normal at C, the shear at C, and the moment at C. Okay, now like with any statics problem, we start out, we want to find the reactions. Okay, and so I'll leave that kind of as an exercise for you on this particular problem. All right. I do need to point out one thing that I overlooked on the original picture, and that is this 9 kilonewton meter. There is an applied moment acting at the pin location as well. Okay, so that's what this 9 is. It's here. I had missed that when I saw it, and so that's why I was kind of looking at it. All right, so for the reactions, we can find those fairly easily. I'm going to sum moments about my point D, which is this point here. Okay, and so I'm going to take a positive 9, plus 6 times its distance of 6 gets me 36, and then minus my AY reaction multiplied by 9. So all of this is coming off of this picture, right? And there should be a moment in the amount of 9 kilonewton meters there. as we start to kind of look at it. All right, and if I do that, I find out that my AY reaction is 5 kilonewtons acting up. Okay, all right, so now we can go in and we can start figuring out, well, what's going on at these particular points. And so it's pretty straightforward. All right, and so all we're going to do is we're going to cut through the point that we're interested in. So if I'm cutting the beam at B, which if you remember was that point just to the left of the point load up here, then my free body diagram looks something like this. I have my AY reaction, which was the 5 kilonewtons, okay, and then I have these 3 forces as we defined them before. I have counterclockwise moment, I have a tensile normal, okay, I think I called it an A here, but it should be an N. Okay, and then I have my VB positive acting downward. I assumed everything positive, so if I get a negative sign in my calculations, I'll know that my picture is wrong. All right, no major deals. All right, so if I do my sum of forces in the X, we're going to find out that the normal at B is equal to 0. I have the sum of forces in the Y direction on this picture is going to be positive 5 minus VB equals 0. VB is 5 kilonewtons. Okay, and then if I do my sum of moments at B, that's going to be then a minus 5 times 3, okay, plus the applied moment at B, and then the normal and the shear are all multiplied by 0 because they're at the point that I'm looking at. And when I do that, I find out that the moment is 15 kilonewton meters. Okay, and it's a positive value, so it's in the direction of what we assumed. Okay, now let's go draw the free body diagram of the point just beyond that 3 meter mark. Okay, now you'll notice that what happened is that when I crossed from 2.9999 over to that 3.0001, now I've picked up this point load because this guy is located at exactly 3 meters. All right, everything else is the same. So I'm going to put my sign convention on here as counterclockwise positive for MC. I've got my NC for the axial, and then my VC is positive downward again. All right, and so just like before, okay, the NC is 0. Okay, sum of forces Y equals 0. I have 5 up, I have 6 down, minus VC. VC is now a negative 1 for the shear on that particular one. Okay, and then the moment in a similar fashion now is going to be equal to minus 5 times 3. I do technically have a 6 on this one, but that's going to be 6 times that really, really tiny, almost 0 number. All right, so this guy does not add to the moment at that point because it's like 0.0000 all the way out 1. Okay, and so if I do that, then the MC on this then is 15 kilonewton meters again. All right, now if you look at this, all we did was we moved one little point, okay, and you'll notice that the normal at B and the normal at C are still the same, and the moment at B and the moment at C are still the same. But look at what happened to the shear. Okay, to the left of the load, I'm sitting up here at plus 5, and then as soon as I cross over the load and get to that next point, I instantly drop down to minus 1. All right, now if you look at the difference between these here, the amount of this is minus 6 kilonewtons is the difference. I go from plus 5 here down to minus 1. That's a minus 6. Well, look at the value of the point load. Okay, it is a 6 kilonewton force in a minus because it's acting downwards. Okay, so if we look at that, all of a sudden we can start to say, well, anywhere that I have a concentrated load hitting this thing, my shear is going to change by the amount of that concentrated load in the direction of that concentrated load. So what we can do is we can start to say, all right, well, if I'm not on the beam, my shear is 0. And as soon as I hit this point, all of a sudden I go right past it, that 5 kilonewton force is going to move me up to a positive 5 shear. Okay, and this starts to allow us to create some relationships that allow us to quickly draw the characteristic equations for shear and moment and axial force for a beam. And now we'll talk more about that in our next video. But that's a pretty powerful observation here, okay? And we'll take advantage of this quite a bit, okay? But that's basically all there is to being able to find these internal forces, is getting the sign convention right and then writing our equations accordingly. All right, now, we talked, suppose we are the designer of record for this beam. Now, I'm going to modify the beam just a little bit. You'll notice I took off the moment at D. I just want to kind of play around with the process more than including that moment in there. Okay, but if we do that, this is basically the same beam without the moment. Okay, I'm putting a 6 kilonewton force on the beam, 3 meters from the left and 6 meters from the right. Okay, I'm going to call A as this reaction, D is this reaction. And if I go through and refine my support reactions, I'll find out that the AY here is 4 kilonewtons up, and my dy here is 2 kilonewtons up, and then of course AX is 0 because there is no horizontal force on this thing. Okay, now we said that we solve all these problems from left to right. Okay, and so what we want to do is I want to introduce you to a concept called the generalized equations for shear and moment. Okay, and what that does is it allows us to quickly determine the equations of all of the shear and all of the moments at all points within the cross section. Because right now, you know, if I'm a designer on this thing, this load's fairly simple. I know the maximum is going to be here, right? But if this load were something more complex or more complicated, okay, maybe I don't know where that maximum value is. Well, as a designer, I want the worst value. I want the maximum to design for, because if I'm good for it, I'm good for everything else. Okay, but what this is going to do is this generalized equation is going to allow us to set up a methodology that will let us start to look at writing equations for big regions all in one shot. All right, so what we're going to do is we're going to break this into pieces. Okay, and I'm going to define a region here. We'll call this as region 1. Okay, and I'll call this as region 2. Okay, and we'll talk about how we know where to write the regions in our next video. But for now, let's just say that region 1 is the region of X between the values of 0 and 3 meters. Okay, and so if I go and I draw a free body diagram and I do an arbitrary cut, whether it's at this point or at this point or at this point, what happens is I get the same free body diagram, right? Whether I'm cutting it clear over here by the load or I'm going all the way up to the 6 but not quite to the 6, it's the same picture, right? It was a 4 kilonewton reaction up, it was a shear force down, an M counterclockwise here, and an N positive, you know, for tension for the axial force. All right, and the only difference is that dimension right there. Okay, because whether it's 0 or whether it's 1 or whether it's 2.999, this is the picture. It's the same picture for all of the cases. All right, so what I can do is I can now write out a set of equations in terms of this X parameter. All right, so if I take my free body diagram, it's still a valid free body diagram. So I'm going to do sum of forces in the X equal to 0, to the right positive, Nx is 0. Okay, and so this Nx is 0 at all points in this range. So I know that there is no axial force on this member from 0 to 3, or 0 to just before 3. Okay, okay, great. Now likewise, I can do the same thing for the sum of forces in the Y. If I assume up is positive, I have a positive 4, I have a minus Vx, and all that has to be equal to 0. So Vx is at 4 kilonewtons. Okay, and again, this is for any value of X between 0 and 3, which is kind of cool. All right, and then similarly to that, I can then go and do my moment. Okay, and so if I sum moments, and generally I write my moment equation at the cut because that lets me get rid of the Nx and the Vx. And I do that for a couple of reasons. Okay, one of the reasons is that if I were working this problem and I made a mistake up here and up here, all right, if I were summing moments at the other end, which you could do, I have to be sure that these numbers were correct, that I didn't make an error somewhere. All right, but if I go through and I sum moments here instead, regardless of what I did in the earlier steps, these guys will not affect my answer. Okay, now I still have to be right on the support reaction, but generally speaking, that I can do that. It's these guys that get a little bit more complex sometimes, you know, in other examples. This example, not so much, but that's one of the reasons that I sum moments at the cut. Okay, now for the moment equation, then it's going to be minus 4, you know, which is the reaction. Okay, and it's minus because I'm going clockwise, and I assume counterclockwise positive again. And the distance to the 4 is this X parameter. Okay, and so that gets me a minus 4x, and then I get the concentrated effect of the internal moment at that location, plus mx equals 0. So my equation now is mx is equal to plus 4 times x, okay, where x is in meters, and then the 4 had a kilonewton units assigned for it. Okay, so what that tells you is that's telling you that the moment within this first piece is changing with x. Okay, and so if I run a couple of cases at x equal to 0, the moment is 0. I plug 0 in for x, that's a 0 value. Okay, if I choose to pick up a point at 1 meter, the moment is 4 kilonewton meters. If I go to 2.9999, then I'm basically getting a 12 kilonewton meter value at the location right before the point load. Okay, and so we can almost start to plot this thing. And so I can tell on this pattern within this range, I can quickly see what's the peak value. Okay, and the peak value is the 12 kilonewton meters occurring at that location. And so now I've analyzed that entire left half of the beam, and I found the maximum shear, I found the maximum axial, and I found the maximum moment, all by writing generalized equations. All right, so let's try one more. Let's go do the other half of it real quick. Okay, and if I look at it, it's the same basic picture. Okay, except now I've gone into a region somewhere over in region 2. So this was my region 2 over here. Okay, and so here's my 4 kilonewton reaction. It's 3 meters. Now the point load is back because now I'm beyond. I'm looking at a region that's between 3 less than or equal to x less than 9. Oops, less than right there, less than 9. And that's the free body diagram. And it's the same picture whether I'm at 3.0001 or I'm clear out at 8.99999. It's still that picture. Okay, and so just like before, we're going to define our reference at the left end. So that's the direction I'm measuring x, and that's my reference. Okay, and so at this cut location, again, for whatever value, this is the picture. Okay, I'm x from here to here. I'm 3 meters from my reaction to the 6 kilonewton applied load, which means then that the rest of the remaining distance is x minus 3. Right? It's this total bit minus the 3 here. That's the piece that's left. Okay, and so when I do that, then I can go in and just like before, I can write my equation. Then we can see that the sum of forces in the x is 0, in x is 0. Okay, for the vertical, sum of forces in the y is 0. I can do 4 kilonewtons up, minus 6 kilonewtons down, and minus Vx, all equal to 0. So Vx is minus 2 kilonewtons. Now, if you go back and you look, kind of like what we showed in the last example, on there, I was at a plus 4 before the point load, okay, and I was at a minus 2 after the point load. So I went from plus 4 to minus 2, whoops, minus 2, that's a minus 6, that's the value of the point load. That logic still works, okay? And then finally, we can come and we can do the moment. Now, this guy gets a little bit more complex, but again, it's doable. All right, so all I'm going to do is I'm going to take minus 4 times x because it's, again, clockwise times x. Okay, and then I'm going to take my 6, and its distance is now this x minus 3 character that we're playing with. And it's positive because it's wanting to go in the counterclockwise direction. So plus 6 times the x minus 3 meters distance plus mx, all equal to 0. And so mx is equal to a minus 2 kilonewtons x plus 18 kilonewton meters. And that's if I do the algebra and expand all of this out. Okay, so again, we can start to test this thing. And now again, it's only valid between 3 and 9. Okay, and so we could do like we did before and we could build a table of this, but maybe instead we want to do something a little different. Okay, so let's try it. Okay, if I go through and I plot all of those equations that we had, okay, if you look at it, between 0 and 3, the shear was positive 4. So at every point along here, I had a shear of positive 4. Okay, and then in the second region, so again, this is region 1, this was region 2, okay, we jumped down to minus 2, and then I was at minus 2 for every value because it wasn't varying with x, it was a constant value. Okay, and again, what we noticed was at this location, the jump from here to here was the same as the point load. So I was at positive 4 down to minus 2, that's the minus 6. Okay, but it also works for the support reactions. The support reaction at A was a positive 4. Right, so if I assume I start out at 0 and I come across and I hit that first point load, it now jumps me up to positive 4. Okay, and then I'm constant all the way across, and then I jump down because of that point load, and then I come across, and then, oh, look, I have another point load here. Okay, and it's a 2 kilonewton force in the upward direction. And so I was at minus 2, I add positive 2, and now I'm back at 0 as I come off the beam. Okay, and so shear moment diagrams are really pretty cool because you always know if you drew them right or have a good idea. If you don't start at 0 and you don't end at 0, something went wrong. Okay, and so that becomes a real good way to test. Okay, so you should always do that last calculation to test it. Okay, and the same thing for the moment. I should start at 0, I should end at 0. Okay, now for us, we said that we had the equation that this was 4 times x. So that took me from 0, and we built up. It was a linear function. Okay, so 4 times 3 got me to the 12. Okay, and then coming down the equation, we had a minus 2x plus 18, right? So at x equals 3, that's the moment is minus 6 plus 18 okay, is equal to a plus 12, there's the plus 12. It doesn't jump, okay? Okay, but at x equal to 9 on this is now m equals minus 2 times 9 plus 18. That guy is 0, okay? And we know that this is a linear function, an x, and so that's a straight line from 12 down to 0, and that gets me all of the points on this thing very, very easily. Okay, so now with those pictures, okay, and this is how I start every design problem, is drawing, for whenever I'm doing a beam design in my profession, that I can look immediately and know what the worst values are. Okay, for shear, I'm going to design for positive 4, and then on the negative side, I'll design for minus 2, and then for the maximum moment, I'm going to design for positive 12, because if I design for positive 12, if it can hold him, it can hold everything else in between. And that's the beauty of what these shear moment diagrams are. Now, there's some other techniques we'll show you on how to construct these, but let's take a look at kind of an interesting relationship that kind of showed up. All right. Okay, so what I did is I went through, and for that should be a 3, and that should be my 9. Okay, that's region 1, and this is my region 2 on here. Okay, let's take a look at those equations that we had for the moments. Okay, we said that the moment in this first region was 4 times x, okay, and that the shear was plus 4, okay. And if I go look at region 2, we said it was minus 2x plus 18, but the shear was minus 2. All right, so the question I have is do you see the relationship between these? All right. Turns out that in all cases, the first derivative of the moment with respect to x is the same as the shear value. And this will always be true for the examples that we're going to work. Okay, and that becomes a pretty interesting characteristic that we can start to take advantage of. All right, if I take the first derivative of 4x, I get plus 4. If I take the first derivative of minus 2x plus 18 with respect to x, 18 is a constant, it's gone. The x goes away, I'm at minus 2. This guy works. Pretty cool. Turns out there's a whole bunch of others in this family that kind of behave this way. All right, when we get to distributed loads in the next lesson on there, okay, it turns out that the first derivative of the shear with respect to x is going to be the same as the value of the load. Okay, now for us, we had a concentrated load. It wasn't a distributed load. Okay, so what happens is that if I had a constant load here, then the shear would be one order higher. It would be a linear load here, and then the moment would be one order higher. So what we've done is that if you remember, if we define a function, as the order of a function as being some x to the n power. Okay, here n is 0, this is n equals 1. Okay, and this is some undefined n, it doesn't really apply. But if this n is a 1, then this n becomes a 2, this n will become a 3. It's a plus 1 between each of these diagrams. So that's one of the reasons that you'll see when we do shear moment diagrams, is that we always start with the actual structure with the load on it. Okay, and then I draw the shear diagram next. Okay, and then I draw the moment diagram next. I can't do the moment diagram without knowing the shear diagram properly when we start to show the other methods that we're going to do. Okay, all right. And so with that, we will end this lesson. This is a big step. All right, the shear moment diagrams for designers, whether you're steel or concrete or whatever your area of choice is, becomes the shear moment diagrams is the first step. Okay, we've got to be able to get those internal forces so that I can do my stress and strain calculations and the things that you'll see in your engineering mechanics. All right, so as always, let me know if you have any questions or any thoughts. Okay, leave them down in the comments down below. Okay, otherwise, stay tuned for more to come. Have a great day. We'll talk to you soon. Bye-bye.